So welcome everyone. I am Shubham Keshri, and this is the problem solving session for the NPTEL course Strategy and Introduction to Game Theory. So before we begin, let me introduce myself. I am Shubham Keshri. I am a PhD student at the Department of Management Sciences, IIT Kanpur. My research work is based on operations research, and specifically I am working in teacher programming. So some key rules for this lecture is, so we will discuss problems, and through those problems we will go through the concepts of that problem, and then we will solve the problem and provide the answer. From your end, you will not be able to see the option of chat, so you can just unmute yourself and then speak. All right, so we'll start. So in the last week's lecture, we had this problem, tragedy of commons, and in this lecture there was some doubt and I couldn't clarify that doubt. So we'll see this problem again, and then we will move on to this week's content. All right, so in this example, or in this problem, there are n individuals, and each individual have a strategy EI, which is from this set 0 to 1, and the utility of all the individual is given by this expression. We are required to find the Nash equilibrium when n is less than equals to 5 and n is less than 5 and n is greater than 5. All right, so this is the problem. So we are having n players. So this is an n player game, and the strategies of this player EI is actually a continuous set from 0 to 1. Now the utility of player I is given by EI minus 5 by n E1 plus E2 plus dot 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 plus En. We can also write this as, so this is actually a sum, so we can write this as EI, and in this sum you will also have an EI, so we'll take this EI outside of this sum, and this factor will be multiplied because it is multiplied to the whole sum, so we'll have EI minus 5 by n EI minus 5 by n, and in this sum we'll have E1 E2 dot 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 EI minus 1. We will not have EI, we will have EI plus 1 dot 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 En. All right, so we can write a short hand of this sum, which will be given as summation of j not equals to I ej. So what does this mean? You are summing j from 1 to n, so it will be j is equals to 1 to n, but j will not be equals to I, and this sum will be E1, E2, E3 and till En, except that term when Ej is equals to En. All right, so we can just substitute, or not substitute, we can just rewrite this expression as EI minus 5 by n EI minus 5 by n summation of j not equals to I j. Or you see, we have an EI common over here, so we can just write n minus 5 by n EI, and we'll just write this as it is, minus 5 by n sum j not equals to I ej. All right, so we have just rewritten the utility function of a player I. For simplicity, not simplicity, we'll just use this expression to come up with the Nash equilibrium for this problem. So the first question is, find the Nash equilibrium when n is less than 5. So you see, for the Nash equilibrium we are required So first of all, this EI is not a continuous set. I'm sorry. In the start of this problem, I said that EI is from a continuous set 0, 1, but it is actually a discrete set which can only take value 0 and 1 and not any other value in between 0 and 1. So we can find the utility of the player I when he is choosing a given strategy. For example, he is choosing 0 or he is choosing 1. So we can write EI when I is choosing 0 and all other player are choosing E minus I. So this is a standard notation and we have seen this notation previously. When you substitute EI in this expression EI as 0, this expression will just become 0 minus 5 by n summation of j not equals to I ej. Alright. And the other strategy of this player is 1. So the utility in that case will become, so here EI will be 1. We will have n minus 5 by n minus 5 by n summation of j not equals to I ej. So these two are the utilities of player I given the strategy of all the other players. Now we have to find the best response of the player I. You see, in this case, when n is less than 5, when n is less than 5, this term, so I'll use a different color, this term, when n is less than 5, this term will be negative. When n is less than 5, this term will be negative. Therefore, this utility will be less than this utility because this second term, this term and this term are the same. Therefore, this strategy will dominate over this strategy. Please understand this very clearly. When n is less than 5, the first term n minus 5 by n will be negative. I hope this is clear. When this is negative, then utility second term, so utility when strategy is 1, this utility will be less than the utility when strategy is 0. So in such cases, this strategy when strategy EI is equals to 0 is a dominant strategy, is a dominant strategy, and this strategy is dominated because the utility is this, then the utility when strategy is 0. Therefore, all the players will play 0. Why? Because I is not special. I can be any player. Therefore, playing 0 is a dominant strategy. It's a strictly dominant strategy. All right. Therefore, the Nash equilibrium when n is equals to 5 is playing 0, 0, 0, dot, 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 0. This is the Nash equilibrium. I hope this is clear. Now the confusion was in the last class when n was greater than equals to 5. So I'll just rewrite all this expression in the next slide and then we'll see what happens when n is greater than 5. So I'll just take the same color, red. We had UI when player is playing 0 and all other players are playing E minus I. So this expression was 0 minus 5 by n summation j not equals to I ej, and UI when strategy is 1 where all the other players are playing E minus j is actually n minus 5 by n into EI. Sorry, EI is 1 here, so I'll just erase this. EI is actually 1, so we'll have n minus 5 by n times 1 minus 5 by n summation j not equals to I ej. All right. Now you see when n is greater than 5, what happens? When n is greater than 5, this term is strictly positive. Strictly positive. And these two terms are same in this expression, right? Therefore, this utility when the strategy EI is equals to 1 is strictly dominant strategy. It is a strictly dominant strategy, or this strategy is strictly dominated. Strictly dominated. Why? Because the utility when a player is playing one. So Roshni, you have joined just now. So what were we discussing? We are discussing this problem in the last lecture. I couldn't clearly explain how the solution of this problem was. So I'm just taking the same problem again and solving the problem, and then we'll proceed for this week's lecture. So what I'm saying is the utility was given as this expression, and we have rewritten that utility using this expression n minus 5 by n ei and minus 5 by n summation ej when j is not equals to I. Now when the player is playing 1 and n is greater than 5, this term is strictly positive and these two terms are same. In that case, you see this utility will always be greater than the utility when strategy is 0. Therefore, this strategy when strategy is 0 is strictly dominated strategy. Strictly dominated strategy. Therefore, playing 1 is a dominant strategy. So, and there is nothing special for this player I. Player I can be any other player. Therefore, 1 comma 1 comma 1 dot 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 comma 1 is a Nash equilibrium for this game. All right, when n is greater than 5. And I have also explained when n is less than equals to 5, you see this term will be strictly negative. In that case, this will be this strategy of playing 1 will be strictly dominant strategy, strictly dominated strategy, and therefore playing 0 will be strictly dominant strategy, and therefore all the players will play 0 and it will be a Nash equilibrium for this game. I hope you understood. Since you joined late, you can just unmute yourself and ask a question, and then we'll proceed. Or you can ask me to repeat the whole problem. Is this okay?
No, it's fine. I think I'll have to check it again. I'll just check it, and if there's any doubt, I'll post in the forum.
All right. So this is from today's this week's lecture. All right. So the first is rationality. So these are very important definitions which forms the basis of game theory. And so we'll start with these basic definitions and then we'll proceed to other problems. So the first, so before going into the definition of rationality, this is a problem which says that we have we have three persons D, E, and F. So this is not a theoretical game at all. This is about relations. All right. So we have three persons D, E, and F, and there is a relation which says that at least as tall as. So in game theory, Professor Vimal has said that that relation is at least as good as. If you remember, this was the relation in the lecture. So I have just modified that relation saying at least as tall as. And I'm saying we have three persons. So for example, we can say D is at least as tall as E, and so on. We can also say E is as tall as F, and so on. So what is the question? This question is about relation. It says that this relation, is it transitive? Is it complete? Is it both? Or more information is required? So this is the question. Think about it for 1 minute and then we can discuss. So what does transitivity say? You should think about in that line. What does completeness say? Think about in that line, and then you will be able to make out what happens.
I think more information is required.
All right. So this you think?
Yeah, because there's nothing about F, right?
Sorry, there's nothing.
There's no information about F.
No. This is just an example. I have just given an example. So suppose what this problem is saying. Suppose there are three person, or there can be n person as well, and you have a relation at least as good as. So if this relation is among these persons, what this relation is actually satisfying? Is it satisfying the condition of transitivity? Is it satisfying the condition of completeness? This is just an example. It can be either way around also. It doesn't matter. You have to say what this relation is satisfying. So for example, greater than sign. Greater than sign is a relation. When I say A is greater than B, I'm using this relation. And suppose I'm also saying B is greater than C. So this greater than sign is actually transitive. It says that when A is greater than B and B is greater than C, then it must happen that A is greater than C. So this relation satisfies transitivity. So in that line, you have to think what this relation will satisfy. Is it satisfying transitivity? Is it satisfying completeness, or something else you think is correct? This is how you have to think.
Then I think it is both A and B.
Okay, it is both A and B. So I have given the example of transitivity. Could you explain what is completeness?
Like we are able to define if one is taller than other.
Right. So when I say A, there is some relation, and B, then there is no ambiguity with this relation. You can completely relate A and B. There is no ambiguity. In that case, it is complete. Therefore, when I say D is at least as tall as E, then you know that E will be either same as D, or it will be have a height less than D. Therefore, it is complete. So the correct answer is both A and B. Is this all right?
Yeah.
All right. So we'll proceed. The second question is about this topic is about common knowledge. By the way, rationality. So this is a very important concept in game theory, where it says, so the definition of rationality is actually given in professor's lecture. You can just go through the definition of rationality. But this is a very important consideration in game theory. Whatever we are doing in game theory, we are actually having the assumption that all the players are rational. That is, they will always try to maximize their utility. They and there are other factors also. I don't remember all the factors, but this assumption is very important in game theory. All right. Now the second problem is on complete information. So here is a situation, and the question is whether this information is complete, mutual, can't be decided, and none of the above. So what is the problem? You see, there is a group of people who has come into a room, and there is a big sign which says the meeting starts at 10 a.m. Now you have to uh, understand this problem and say whether this information is complete or mutual, or it cannot be decided, or none of the above. By the way, Mukesh, the problem which we were discussing in week 2, the last problem, I have solved that problem in this week's lecture at the start of this session. So if you have any doubt, you can just watch that lecture again. This lecture, when I upload, you can watch it again.
Okay, sir.
All right. So in this problem, you have to tell me, is this information complete knowledge or mutual knowledge, or it cannot be decided, or none of the above?
Can it be both?
No, I have not given an option. So obviously that may be, but there is not an option of both.
Okay. Then common knowledge.
Okay, so I have a vote for common knowledge. Why do you think it is a common knowledge?
Because we know that everyone. Oh no, sorry, it is mutual knowledge.
Okay, so the vote has changed
Because we know that we know the information.
Sorry.
Because we know the information.
Right. So these people in the group can see the information in the board or in the wall, right? So you think it is mutual knowledge.
Yeah.
What is the definition of common knowledge?
Like we know that other person in the room also knows the information.
Right. So you see, common knowledge, in simplicity, you can just write every player knows that, and you can just raise it to k. Every player knows it is true. So this is the definition of common knowledge. All right. So it says that every player knows, and it can be raised to any power. So you can just repeat it k time, or k can be any number between. So it is, this k is as large as you can think. And this is what the definition of common knowledge is. Every player knows that, every player knows that, every player knows that, and so on till this statement is true. So, or statement A. Instead of true, we can say statement A. Now think about this this situation where all the people are in the room and everybody can see that they can see the board. So all the other person can also see the board, and that's because that board is displayed in the wall, right? Am I making sense?
We don't know if, like, in case there are any disturbing that we.
Right. So those situations I have not thought about it. That's why it's not written. So suppose everybody can see.
Oh,
So those I have not written. So it's my mistake.
okay, but generally, if these type of questions are being asked, then it means that we should assume it is a general normal condition. Is it?
Right. So in this case, everyone can see that there is a board saying this statement. Now everybody knows that everybody can see that board, and you can just reason this out k number of times, that everybody knows that everybody can see that everybody can see this board, and so on and so forth, right?
Yeah.
So therefore this becomes common knowledge. So this is the correct answer. Any doubt? So for example, the problem which professor has discussed in the class, where a person is texting, A is texting B to meet. I don't remember the example exactly. So it was like some station at 7 p.m. So A has texted B. All right. Now B confirms by sending a text message back. Confirms. So you see, A has sent a text to B and B is confirming. Therefore, A knows that B knows that they have to meet at 7 this place at this time. Is this correct? Because A has received a confirmation from B.
Yeah.
Right? But it is not the other way. B has not received a confirmation from A because they had decided to meet someplace else. Therefore, B doesn't know if A knows that B knows. So suppose A had given a confirmation. In that case, B knows that A knows that B knows that they are meeting at some place X. But since B has not received a confirmation from A, then B doesn't know that A knows that B knows that they are meeting at place X. Think about it. Since B had sent a confirmation to A, therefore A knows that B knows that they are meeting at some place X. But since A has not sent a confirmation of receiving the confirmation message from B, then A doesn't know. Sorry. B doesn't know if A knows that B know that they are meeting at some place X. Is this correct?
Uh, can you repeat once again?
I know it is confusing. So this is not my problem. This is the problem which sir has discussed. So suppose we had discussed to meet at a place X, but I am changing the venue. I'm saying we'll meet at place Y. So I have sent you a text. Now what you're doing, you are just sending me a confirmation. All right, I have received it. We will meet at place Y. Now I know that you know that we are meeting at place Y and not X. But you doesn't know that I have received that SMS because I have not sent you a confirmation. You are assuming that I have received the confirmation, but you actually don't know if I have received the confirmation or not because I have not confirmed that thing to you.
Yeah. Yeah,
Therefore you don't know if I know that you know that we are meeting at place Y. That is the overall idea.
So
Therefore
this
this is
counts as
not common knowledge.
This is not okay, but it is mutual knowledge.
So mutual knowledge doesn't have any definition. I have just written it here.
Okay.
All right, just for confusing students. All right. So this is one more problem. It says that the players are rational. This fact is what? Is it common knowledge, mutual knowledge, incomplete knowledge, or something else? Players are rational.
Common knowledge.
Why is it a common knowledge? Why are we saying that it is a common knowledge?
Like because we know that everyone knows the like how to play or whatever.
Right. So if you think from the starting of this course, professor was saying that the players are exactly aware of the utilities of the other players. They exactly know if I play this, the other player will play like this. Therefore, everything in this game was common knowledge. We will proceed further when in this course, and we will see some problems on incomplete information as well, where there is asymmetric information. Some players have extra information than the other player. Right? So for this example or for this problem, the correct answer will be common knowledge. Is this all right?
Yeah.
Okay, okay. Just skip this part. All right. So this is actually dominant strategy. Dominant strategy. I was pasting it here, so it came there. Never mind. So this is a two-player game, player one and player two, and the question is find the dominant strategy of player one. So we are trying to find the dominant strategy of player one. Now bear in mind we have two kinds of dominant strategy. First is strongly dominant, or in the other way, strongly dominated strategy, or dominant strategy you can say, STRONGLY, strongly dominant strategy, and the other is weakly dominant strategy. What is strongly dominant and what is weakly dominant? Could you help me with this?
I don't remember.
All right. So you
I
see,
think.
suppose there are n players. So I'll just I would need space. So let me write it first. So suppose there are n players, and I'm talking about player I, and player I is nothing special. So it can be any one of the n players. Right. So when the utility of player I given, he is playing EI star, and all the other players are playing EI minus. So I have not defined what EI star is. I'm just saying it is a specific strategy. For this example, suppose A is EI star. So it can be any strategy for now. So suppose player I is playing EI star and all the other players are playing EI minus. It can be anything. If this utility is strictly greater than UI EI comma E minus I for all EI, sorry, for all EI minus, for all, sorry, for all EI minus belongs to the set. So whatever the set is, suppose EI is the set of, so I'll just explain clearly. What is EI? For this example, so EI is the set of strategies a player has. So for this example, player one is having A, B, C, and D. So player one is having 4 strategies. So this is the set of strategies a player have. So in this case, E1 is actually A, B, C, D, and E2 is actually X, comma Y. All right. So it is the strategy set. E minus I. So apart from player I, what are the strategies other players are playing? So for all the strategies, whatever other player plays, this strategy, the utility which is obtained from this strategy is strictly greater than the strategy of the other player. So for example, in prisoner's dilemma, I can just take the example, confess. So it was actually deny and confess. Um, confess, deny, confess, deny. All right, so if they confess, they will get a utility of suppose 4 comma 4. If they deny, they get a utility of 1 comma 1, and all the other things. Does and yeah, we can write the example, right? So when the one player is denying and the other one is confessing, so he will benefit. He will get suppose 8 comma 0 and 0 comma 8 and 8 comma 0. Have I written correctly? Both, if both confesses, if okay, so this will be the other way around. If both confesses, if both confesses, then they will get a less term in jail, and if both denies, they will get a higher term in jail. All right, so it is 2 comma 2 and 4 comma 4. I hope this is correct now. Now you see, in this game, there is a strictly dominant strategy. I have not written the utilities correctly. Let me go back and write the utilities correctly. Otherwise, this will not make sense. So yes, so I have got the utility. I'll just write the utility from the example. Otherwise, it will not make sense. So the utilities are, for example, 100 comma 100, 150 comma minus 100, minus 100 comma 150, and 10 comma 10. So this is from Cold War game. I have written this example for Cold War game. All right. So this is actually HD, health and defense, health and defense. You can just go back and check. These are the utilities. Now you see in this game, there is a strictly dominant strategy. You see, playing. So when player 1 is playing, so when player 2 is playing H, the strategy which player 1, so this is player 1 and this is player 2. When player 2 is playing H, player 1 should play D because 150 is more than 100. Similarly, when player 2 is playing D, player 1 should play D because 10 is more than minus 100. So you see in this example, this strategy D is strictly dominant strategy. Player 1 will never play H because whether player 2 plays H or player 2 plays D, player 1 will always benefit if he plays D. So this is what it is writing. No matter what the other player is playing, it doesn't matter. This strategy E minus EI star is always greater than equals to EI. Is this clear?
E minus I can be two different.
Anything.
Like,
It can be anything. It doesn't matter.
no, like different on left and right side of the same equation.
No,
E
no,
of
no.
minus I.
These two will be same. So what it's saying is, suppose this is H, this should be H, but it should be for all EI. So we should also check for H, we should also check for D, and if there are other strategies, we should also include those. For all the strategies, this should dominate the other. So for example, I am checking, so I'll just write this example. So we are checking the utility of player 1. Player 1 is playing D and the other player is playing H. All right, so this is of player 1 and this is of player 2. All right, this should be greater than player 1 playing D. Sorry, player 1 is playing any other strategy. So suppose player 1 is playing H. So player 1 is playing H and player 2 should play the same strategy over here. All right, now this is true. You see, 150 is greater than 100, but we should check this for all the strategies of player 2. Therefore, we should also check this for D. This is greater than H comma D. All right, player 2 strategy. What I am doing, I am saying first we'll fix player 2 strategy as H. So in this example, I have fixed the player 2 strategy and I am saying this strategy D for player 1 is the utility for this is more than when he is playing H. Similarly, when I fix this strategy for player 2, which is D, this should also be greater than H. Therefore, for any strategy of the other player, this strategy D is always better. So player 1 will never play H. He doesn't have to play H anytime. He will always play D. Is this all right? because whatever strategy the other player is playing, he's always better off playing D. Is this correct?
So this is same as best response.
Yes.
Okay.
So you see, when I am saying best response of player 1 given the other player is playing H, so this is for 1. So over here the best response is D. Best response
Okay.
of player 1 when player 2 is playing D is also D. So for all the strategies of second player, the best response is D, right?
Yeah.
Therefore, D is a dominant, strictly dominant strategy.
Okay.
So for if the best response of one player is always the same for the responses of the other player, therefore that strategy is strictly dominant strategy.
Okay. Then what is just dominant?
Right. So there is something called weakly dominant strategy.
Okay. So there is nothing called just like I
No.
remember seeing in previous lecture something called
So
just dominant.
when we just say dominant, we are implying strictly dominant strategy.
Okay.
We
Okay.
will specifically mention weakly dominant when we are trying to mention weakly dominant. We'll never say weakly dominant as dominant, but when we are saying
Okay.
dominant, we mean strictly dominant strategy.
Oh.
All right. So this is what strictly
Yeah.
dominant strategy is, and weakly dominant strategy. The definition of this is actually I'll write the definition for better understanding. So you see, it says that I'll just change the color. It says that UI EI star. So EI star can be any strategy because we are writing a general term. That's why I'm writing EI star. E minus I is greater than equals to EI. Sorry, UI comma EI. I'll just write it so it's better. For all E minus I belongs to capital E, and I'll write minus I. Right. But this and so what it says is the utility can be either same or greater than equals to the other utilities, but there should be one specific strategy. There should be one specific strategy for which this relation holds for strict equality. I'll give you an example. So what does it say? Suppose in this example, I'll just erase this for it now. I'll take one example. So H D H D, and suppose there is some other strategy R. All right. So I just write those 100 comma 100, 150 comma minus 100, minus 100 comma 150, 10 comma 10, and suppose this is 20 comma 20. 20 comma 20 and 20 comma 20. So you see, in this case, suppose the second player has three strategies. Now, when the second player is playing H, the best response of player 1 is to play D, because the utility is strictly greater than what he will get when he plays H. In this example also, this is strictly greater than, so in this strategy it is strictly, but in this strategy it is same. So what this weakly dominant strategy says is, suppose there are some strategy where we can say it is greater than equals to, but there should be one strategy where this strict inequality holds. So in this case, there are two strategies where strict inequality holds, but there should be at least one, and therefore D will weakly dominate H. Is this correct or clear? I mean,
Yeah.
it says that D is at least as good as H, not worse. It is at least as good as H. All right. So I'll just erase. I shouldn't erase this part, I guess. Okay, I'll not erase this part. So the game is you are given two players, player 1 and player 2. You have to find the dominant strategy of player 1 in this example. Please try to find a dominant strategy of player 1. I hope you have a pen and a paper. You should try this out, then we'll discuss.
Here there is no strict, strongly dominant stuff.
All right. So you're saying there is none.
No,
This is
yeah, okay.
none. That is what it means, right?
Yeah.
So you see, you are correct. You can just check 5. When you see when player 1, player 2 is playing X, you see 5 is greater than 3 and 4 is greater than 3. Therefore, you can just say that B is dominated by A. All right, B is dominated by A. So you can just remove B. B will never be played because it is strictly dominated by A. Is this all right?
Yeah.
Now you just check for the other. When A and C you are comparing, so 5 is greater than 2, but 4 is same as 4. So A and C, so A is weakly dominating C. So I'll just write it somewhere. A strongly dominates B. Therefore, B will never be played. Because you are better off playing A. Why will you play B? Alright, B will never be played. Again, you see, when you compare A and C, this 5 is more than 2, but 4 is same as 4. Therefore, A weakly dominates. You see, in this case, it is same, but this is strictly greater than 2. Therefore, A weakly dominates C, not the other way around. All right. So A weakly dominates, I guess, weakly dominates C. All right. Now, when you compare A and D, you see 5 is greater than 4, but 4 is less than 5. So A neither weakly dominates nor strongly dominates D. Therefore, both A and D, so there is no relation between A and D in terms of strongly domination and weakly domination. So you cannot find one strategy which is a dominant strategy. Therefore, there is no strategy which you can say is dominant. There is no one strategy which is dominant. Is this all right?
Yeah.
Okay. In this game, we are talking about now player 2. So what is one strategy which is dominant strategy for player 2?
Why I think.
So you're saying why is one strategy which is dominant? Are you sure?
Like it is weakly dominant in one case when in a when I player one being played.
Okay. So what do you say? Is this statement correct?
Why is I think it is right.
So you see, V is actually not a dominant strategy. Y weakly dominates X. Y weakly dominates X. You see, when player 1 is playing A, player 2 is better. Player 2 is indifferent of playing X or Y. He can either play or X or play Y. The utility is same. When player 2 is playing B, player 2 would prefer playing Y because utility of Y is more than utility of X. When player 1 is playing C, player 2 is indifferent of playing X or Y because the utility of both of them are same. When player 1 is playing D, player 2 will play Y because the utility of Y is more than utility of X. Therefore, you see, In some of the strategies, the utility is same, but in some of the strategies, the utility is strictly higher. Therefore, Y weakly dominates X. Is this statement correct? You're not audible now. Yeah, you're audible now. All right. Therefore, this is not a dominant strategy. This is a weakly dominant strategy. That's why I have given this question over here to clear the definition of strictly domination and weakly domination. Therefore, Y is a weakly dominant strategy. Dominant strategy. All right. So this is a interesting question. I'll not say difficult. It's an interesting question. So this is a prisoner's dilemma, and you know the definition of weak dominance and strong dominance. So I have written SDSE, SDSE, and WDSE. So I'll write the full form. SDSE means strongly dominant strategy equilibrium and weakly dominant strategy equilibrium. So what does this two equilibrium mean? So for example, that we had taken the Cold War example. I'll just write the table again. Cold War. So in this Cold War, we had that a country can either uh, invest in health or defense, health or defense. My screen is visible, right? All right. So when both of them are playing health, the utility is 100, 100. When one is playing defense and the other one is playing health, so the one who is playing defense will get a higher utility, which is over here 150. All right. And when both are playing defense, then they are getting 10, 10. So this game table is here, and we know because we had just discussed this. This is the best response of player one, and when player 2 is playing H, and this is the best response of player 1 when player 2 is playing D. All right, this is player 1 and this is player 2. Again, on the other hand, so therefore this strategy is strongly dominant strategy. Dominant strategy. All right. Now, when player 1 is playing H, player 2 will prefer playing D, and when player 1 is playing D, player 2 will prefer playing D. Therefore, this is also a strongly dominant strategy. Is this all right? You can just unmute yourself. Yes. Therefore, you see where the strongly dominant strategies meet. This intersection is known as strongly dominant strategy equilibrium. It is also a Nash equilibrium of this game, but this is also known as strongly dominant strategy equilibrium. Similarly, if we had this weak dominant strategy as D, for this example, it is not true. Suppose D was a weakly dominant strategy and this D was also a weakly dominant strategy. So the intersection of these two strategies will be known as weakly dominant strategy equilibrium. Is this clear? Strongly dominant strategy equilibrium and weakly dominant strategy equilibrium.
Yeah.
Now we have a game where the utility I have just given, which is unknown, X, and you have 4 questions. The first question is find X such that confess. So C, C is just confess. I'll write it. Confess, confess is a strongly dominant strategy equilibrium. The first question is this. Think about it and then we'll see how we'll tackle this problem. Or if you know the answer or you have found out the answer, you can just unmute yourself and speak. Then we'll discuss. You see, if you are getting a specific value, you can state a specific value. If x satisfies a range, you should specify a range. It depends upon the question. If x is satisfying a range, you should give a range. If x is satisfying one specific value, you should give a that specific value.
I think x less than 2.
X less than 2 for A. Now let's see if this is true or not. All right, then we'll move on to A, B, C, and D. So you see, what are we trying to say? We are trying to say that confess is a strongly dominant strategy for player 1 as well as for player 2. So for confess to become a strongly dominant strategy for player 1, minus x should be greater than, so we are doing it for player 1. Let me write it clearly. So we are doing it for player 1 now. So we are just doing it for player 1. So for x to be a, so this strategy confess to be a strongly dominant strategy, the utility for player 1 when player 2 plays other strategies should be strictly greater than the deny. So this minus x should be strictly greater than minus 4. So this is when player 2 is playing deny, player 2 is playing deny, and in this case minus x should be strictly greater than minus 2 when this is for player 2 is playing confess. Now if you just change the sign, it is x is less than 4 and x is less than 2. Is this correct?
Yeah.
So when x is less than 4 and x is less than 2, which range will satisfy both this equation? So you see, what are we saying? Yes, yes. So for everyone, I'll just explain this, what it means. So this is 0, this is a number line, and I have marked 2 and marked 4. So what these two expressions says is x is less than 4. So it can be any value. It can be any value less than equals to 4. The second expression says that x is less than 2. So it says that any value less than equals to 4. So when this equation, when it satisfies, the range should be common between both the two because both equations are satisfying. Therefore, x is less than 2 is the range for x when confess becomes a strictly dominant strategy for player 1. All right. So x is less than 2. Is it true for player 2 as well? If you check, you will get the same equations, and therefore x is less than 2 is also true for. So I have written x, so it is actually an indication that the values will be same. And if there is some discrepancy, suppose I have written 2x over here, you should check if that value is actually making the other player's strategy a strictly dominant strategy or not. All right. So it is not strongly dominant, it is strictly dominant. Right? So this is not strongly, strictly. So if this thing is not x, for the second player it is something else, 2x, 3x, or x plus something, you should go in the second player's area. You should just say player 2 and then check for player 2, and then you have to check which value of x is satisfying all the equations for player 1 and for player 2 as well. In that case, you will be able to say the correct value of x, which makes C comma C a strictly dominant strategy equilibrium. Am I making sense? All right. So for player 2 also, I'll just do it again. So suppose player 2, for player 2, when player 1 is playing deny, this minus x should be greater than minus 4 because confess will become, then only confess will become a strictly dominant strategy. So minus 4 should be greater than minus x should be greater than minus 4 when player 1 is playing deny. And for second case, this minus x should be greater than minus 2. So minus x should be greater than minus 2 when player 1 is playing confess. And these two equations are exactly the same as these two equations. Therefore, we will just say x is less than 2 is that value of x. These values of x will make confess as strictly dominant strategy equilibrium. Suppose these two equations were something else, you have to satisfy all the four equations, and those values will qualify as the value which makes confess as strictly dominant strategy equilibrium. I hope I'm making sense. The second question over here is, all right. The second question over here is, what is the value of X which makes confess a weakly dominant strategy equilibrium?
It should be X less than or equal to 0.
Right. So for everyone else, I'll just show this. So you see, these two equations will be same, but over here, when we are saying weakly dominant strategy, so the utility can either be greater than or equal to, right? But for one, it should be strictly greater than. So it can either be for this or this. It doesn't matter, but it should be for one. At least one should be strictly greater than greater than. So you see, when x is less than 4 and x is less than 2 was for strictly dominant strategy. Now when you say x is less than equals to 2 and x is less than 4, over here you see, for one case we have a less than equals to sign. For the other case we have a strictly less than sign. All right. Therefore, these two equations will indicate that you are in the dominant strategy part. So you see, when you find a value of x which satisfies these two equations, so what you have some relation, x is less than 4 and x is less than 2. So this was for a strictly dominant strategy. All right. Now you are trying to find out a weakly dominant strategy. So either for this or this, an equality should be there. So if you see, if you put an equality over here, then these two equations will become infeasible. Therefore, the equality will not be here. The equality will be here. And hence, x less than equals to 2 is a weakly dominant strategy equilibrium. We have a strict inequality for one and a less than equals to sign for the other. Therefore, x less than equals to 2 is a weakly dominant strategy equilibrium. So for those who are not here, you can just post a question in the discussion forum if you are facing any trouble in these problems. All right. The third question is, find x such that c comma c is a weakly dominant strategy but not strictly dominant strategy. What will be that value of x for which c comma c is weakly dominant strategy but not strictly dominant strategy? Right. So that value will be x is exactly equals to 2. So when x is exactly equal to 2, you can just draw the game table and check. So the game table will become -4 comma -4, -2 comma -2. This is because we are putting x as 2. It will be -2 comma -2 and -2 comma -2. So this is deny. This is deny. This is confess, deny, confess, and deny. You see, when player 2 is playing deny, player 1 can play confess, but when player 2 is playing confess, he can either choose C or D. Therefore, there is no strictly dominant strategy. All right, there is no strictly dominant strategy. The utility is becoming same. Therefore, it is a weakly dominant strategy, but not a strictly dominant strategy. And the last question is, what is that value of x? In which case, it is not even a weakly dominant strategy. Therefore, it is neither weakly dominated nor strictly dominated. What will be that value? Right. So when x is greater than 2, then so you can just put any value, dc -4, and in place of x you can put any value greater than 2. Suppose we are putting 5. So 5 comma -2, -2 comma 5, and 5 comma 5. So if you write the best response, so the best response of player 1 when player 2 is playing D is 5. The best response of player 1 okay, strictly greater than 2, so it should be -5. I'm sorry, because it is strictly greater than strictly greater than 2, and since we have a minus sign, so it will be -5. in all the places. Now you see, this strategy is not, this is not actually the best response. The best response is to play D. So this is not the best response. And in the other case, when player 2 is playing confess, just a minute, I'm being confused. I'm getting confused. So I'll just draw the game table again. You can help me if you are finding out what is happening. Right. So I have taken a value strictly greater than 2, which is -5 over here, and I have put the values correctly. Right. So when player 1 is playing D, when player 1, you can just help me also. All right. So when player 1 is playing D, player 2 is better off playing D. Right. When player 2 is playing C, player 1 is better off playing 2. Right. When player 1 is playing D, player 2 is better off playing D. And when player 1 is playing C, player 2 is better off playing D. Therefore, confess is neither weakly dominated or strongly dominant strategy equilibrium. In such cases, this becomes the Nash equilibrium, and actually that is the strongly dominant strategy equilibrium, because deny becomes the strictly dominant strategy for player 2 and for player 1. Therefore, D comma D becomes strictly dominant strategy equilibrium in that cases. Therefore, this C comma C is not even a weakly dominant strategy equilibrium. Is this clear?
Yeah.
All right. So this is another topic which professor has covered. This is iterated elimination of dominant strategies. And using this method, we will try to find out the Nash equilibrium. So over here we have two players, player 1 and player 2, and both of them has 4 strategies each. And I have given the game table. Please try to find out the Nash equilibrium of this game by iteratively eliminating the strategies of the player. So for example, in over here we had eliminated B because B was strongly dominated by strategy A. In such cases, we actually eliminated the strategy B. Similarly, you have to eliminate the strategies iteratively and come up with the equilibrium for this game, Nash equilibrium for this game. Please try to do it. This is a little bit tricky problem, so do it very um, attentively.
Can you once go back to the previous example where we say A was strictly dominating B?
Yes. So this was the example, you see. So do you want me to explain, or is it all right?
No, I got it. Yeah. Thanks.
Should I go back to the problem?
Yeah. The problem is okay.
Why are these type of problems tricky is because there is some relation on how you are eliminating strategies. All right, so that flow, if you don't find out, then it will be difficult for you. It is not difficult per se that the problem is difficult. You have to identify which one to eliminate, and then it just flows. So that identification for the first thing is important.
Iterative elimination, how do we do it? Like,
Okay, so you see, for this example, or for this example, so we had Cold Wars. I have more Yes, so over here I had a Cold War example. Now that we have the game table, so we can just say health and defense, health and defense. The problem was 100 comma 100 minus 100 comma 150, 150 comma 100 and 10 comma 10. Now you see, you have to identify a dominant strategy, and this additively elimination method only works for strictly dominant strategy. We cannot do this for a weakly dominant strategy. So you have to identify either you have to identify strongly dominant strategy, and it is better to identify strictly dominated strategy. When you identify strictly dominated strategy, then only you can eliminate that strategy. So instead of identifying strictly dominant strategy, we will try to identify strictly dominated strategy, and then we will eliminate those strategies. All right. So in this example, we have two players, player 1 and player 2. First, we'll try to reason out for player 1. So you see, H is actually, when player 2 is playing H, this strategy is dominated by strategy D. Similarly, when player 2 is playing D, this strategy is dominated by strategy D. Therefore, H is actually strongly dominated by strategy D. Is this all right?
Yeah.
So we have eliminated strategy H for player 1. Now we can reason this out for player 2. When player 1 is playing D, there is no other strategy for player 1. Then player 2 is better off playing D instead of playing H. Therefore, we can eliminate H completely for player 2 as well. And we have been left out with D comma D, and therefore this is the Nash equilibrium. This is how iterative elimination works.
This is in the case where there are only 2+2 games. If
Yes.
there are 4+4 games, do we have to strike out one from player 1 and then one from player 2 and then
it is not important of shuffling from player 1, player 2, player. If you can eliminate more strategies of one player, then you can just go on with that as well.
okay.
But you should only eliminate. Yes, then you can check for player 2. And more importantly, you should only eliminate strongly dominated strategy.
Okay.
And if you have seen professor's lecture, have you seen professor's lecture?
No, I haven't seen this.
Okay, so in that case, let's see what happens. You just try and then we'll see.
Okay. Here, D seems to be strongly dominated by C.
All right, correct observation. So you see, when player 1 is playing C, this utility is more than this utility is more than this utility is more than this, and this utility is more than this. Therefore, you can eliminate D. All right. Next, this is iterative elimination. You have just eliminated one, and we can just move on and on. So you have to try.
I don't think there is anything else in player 1's which we can help.
Try to find out for player 2 then.
Okay. Q is strongly dominated by R.
Okay, then we'll just see that. So this is more than this. This is more than this. This is more than this, and you don't need to check for D because D has been eliminated. Therefore, we can just eliminate Q altogether. All right. Next.
Uh, C is dominated by A. Sorry,
B
sorry.
is
A is dominated by C. A is dominated by C.
not so. A is dominated by C. You see, mine. Okay, okay. For player
Now
one,
we
right?
are
Player one, right? So 0 is more than -3, 4 is more than -1, and 0 is more than -2. All right. So A will be eliminated.
S is dominated by R.
S is dominated by R. 3 is more than 0. 4 is more than -1. All right. So we'll just eliminate S.
Okay. B is C is dominated by B.
Okay. For player 1, you see 2 is more than 0. Over here, 2 is more than 0. So we can just eliminate C.
Okay. Now T is sorry. R is dominated by T.
Okay. For player 2, 5 is more than 3. Therefore, R will be eliminated. Therefore, we have actually achieved that this Nash equilibrium, which is B comma T. Is this all right?
Yeah.
Now, just to check, we will do this for check this again with using best response logic. All right. So this we have done using eliminating the dominated strategies. Now we'll do this again for best response. All right. So you can just help me again. So when player 2 is playing Q, what is the best response of player 1?
A.
The best response of player 1 is A. When player 2 is playing R, what is the best response of player? Sorry, when player 2 is playing R, what is the best response of player 1?
B.
B. Okay. When player 2 is playing S,
C.
C. The best response of player 1 is C. When player 2 is playing T, what is the best response of player 1? B. Again, we'll check for player 2. When player 1 is playing A, what is the best response of player 2?
S.
S. Okay. I'll just mark it with different color. S. When player 1 is playing B, what is the best response of player 2?
T.
T. When player 1 is playing C, what is the best response of player 2?
R.
R. And again, when he's playing D, what is the best response of player 2?
R and T both.
R and T both. All right. So you see the best responses are intersecting at B comma T. And therefore it is a Nash equilibrium. All right. So the best responses are intersecting at um, this pattern. So this is a problem on second priced seal bid auction. Second price seal bid auction. So this I had discussed in my first week's lecture, if I'm not wrong, because there was a problem on week 1 assignment for second price sealed bid auction. So I hope that time I could discuss it clearly. So have you seen those lectures?
Yeah.
Okay. So this is just a simplification of that problem again. It is not the complete second price seal bid auction. Professor has discussed in depth about how the second priced seal bid auction is behaves. And there was a question by Mukesh in the discussion forum, and he was asking, so if all the players are bidding some amount, BI, and the buyer he will be better off taking the highest bid and not the second highest bid. His doubt was that. So because whenever some person wins and in first prize auction, he has to pay whatever he has bidden, and that is the highest amount. But in second prize auction, he has to pay the amount which is the amount highest among the bids of other players except him. So that will not be the highest bid, may not be the highest bid. So his doubt was, why will such auction be played by a buyer? Is the doubt clear? Because in second prize auction, the buyer is getting the second prize and not the first highest bid, right? So why this is critical, well, not critical, I would say, why this kind of auction is being played is being discussed in depth in the professor's lecture, where he explains that this kind of auction actually reveals I am very bad at spelling, so just excuse me. All right, reveals the true value of the players. It reveals the true value of the players. All right. So you can just watch the lecture for explanation why this kind of auctions are actually reveals the true value. It will be clear. So in this problem, we are not going on how this is revealing the true value. In case you have doubt, we can discuss in the next lecture. But this problem is about two players, Rahul and Rohan, and they are competing in a second bid auction. You can just take a minute to read this question. So have you understood the problem?
Yeah.
So it is saying the bid must be in multiples of 5. So it can either be 5, 10, 15, and so on. The maximum amount each bid can be is 30. So there is a maximum amount of 30. So these are the strategies a player can play. He can either play 5, 10, 15, so on till 30 in multiples of 5. The valuation of the painting for one player, Rahul, is $10, and for Rohan it is $15. What is the value of payoff corresponding to both players when they bid their maximum valuation? So they are bidding their maximum valuation. So Rahul is bidding $10, and Rohan is also bidding his true value, which is $15. All right. So I'll just write B1 and B2. Now, what are their payoffs? Could you tell me what are the payoffs of both the players?
0 and 5.
0 and 5. So could you just walk me through why 0 and why 5?
Because Rohan is going to win the bid and he will have to pay $10 because that is
So
the second highest.
right, so he is the winner and he has to pay the second highest amount. So his utility, so utility U2 will be, what is his true value? The true value is 15, but he's paying only 10. So he's just paying 10. So the utility is coming out to be 5. But since Rahul is not winning and he has to pay nothing, therefore the utility of Rahul is 0, and therefore 0, 5 is the correct answer. All right. So since you have not seen the lecture, we need to discuss on this problem. Before that,
Actually,
you
it's
could,
fine. I have to go now, so I'll watch the lectures this part later.
no problem, you can leave.
Thank you.
So this is a problem on traffic at equilibrium. We have four people and there are they have to drive from A to B. So we are having a route from A to B. Now there are four people. So this is very important. You have to see that there are four people and they need to drive from A to B at the same time. Everyone must choose which route to take. So there are different routes to go from A to B. Two routes are, just ignore this part. Two routes are available, one via X and one via Y. So one will be via X and one will be via Y. So it can go from A, X, B, or it can go from A, Y, B. All right. So I have written refer to the figure below because I have taken it from somewhere and I have not mentioned the given the figure here. So I'm just drawing it over here. All right. So just ignore this thing for now. Road A to X and Y to B are both short and narrow. So these roads A to X and Y to B are short and narrow. One car takes 12 minutes and each additional car increases the travel time per car by 3 minutes. So when a car is traveling from A to X or Y to B, if there is one single car, that car will take 12 minutes. But since this road is short and narrow, the more cars they are there in this road, the more time it will take to cross this road because there is congestion in this road. The congestion is increasing. So for each additional car, the travel time is increasing by 3 minutes. All right. So if there are two cars, the travel time will be 15 for each because 12 plus 3 15. If there are three cars, then the travel time will be 12 plus 3 times 2, which is 18. So it will be 18 minutes for all the three cars. All right. So this is how this route works, A to X and Y to B. Roads from A to Y and X to B are wide and long. So these roads are long and wide. From A to Y, one car takes 30 minutes and each additional car increases the travel time by 1 minute. So if there is only one car in this road from X to B or A to Y, no, for A to Y, we're talking about A to Y. In that case, one car will take 30 minutes, but for each additional car, the travel time increases by 1 minute. So if there are two cars, both the car will take 31 minutes. If there are three cars, both the car will take 32 minutes. All the three cars will take 33 minutes each. All right, 32 minutes each. 32 minutes because 1 minute is increasing per car. Additional 1 minute. Okay. Now from X to B, one car takes 30 minutes and each additional car increases the travel time by 0.9 minutes. We are trying to find the Nash equilibrium of this game. A word of caution, since this is a very small game where the players are only 4, this Nash equilibrium will come in fraction. We are going to round it up or round it down, whichever way it is. If this number 4 cards are higher, suppose 400, 500, 600, then those fractions will make more sense because it will be round to the nearest integer. So this Nash equilibrium will be in fraction, but we are trying to round it to the nearest integer. That is what I wanted to say. Now the question is find the Nash equilibrium. We are given 4 options. Action profile is 2 players take via X and 2 player takes via Y. So 2 players are going from AXB and 2 players are going from AYB. 3 player is going from AXB and 1 player is going from AYB. All the 4 players are taking route X and none of the above. There are some other routes. All right. So these are the 4 options for this problem. Just take a minute, think about it, and then we'll discuss how to solve this problem or move on to solve this problem. So the thing to understand in this problem is that the number of cars which is traveling from A to X will be same as the number of cars which is traveling from X to B, because there is no other route from X. If a car goes from A to X, it has to travel X to B. And similarly for the other route also, if a car travels from A to Y, they have to travel from Y to B. All right. And what are they trying to do? This travel time, they are trying to find out what is the appropriate travel time such that it becomes Nash equilibrium. So those strategies and the utility over here is actually the negative of travel time. They are trying to minimize the travel time. So higher utility means lower the travel time. Right? So take a minute, think about it, and then we'll discuss. Okay, so you see, we are trying to get the utility. All right. So negative of the travel time is the utility. Now we'll just focus on the travel time first. Then we'll see what is the utility. All right. So if a player is taking going from A to X, so a player, not a player, we say how many cars are going from A to X. So A to X is one route, and Y to B is one route, X to B is one route, and A to Y is one route. Now you see, suppose N1 are the number of cars which is taking A to X. So the number of cars which is going from A to X will be same as the number of cars which is going from X to B. So this will also be N1. Similarly, the number of cars going from A to Y, if it is N2, then Y to B, the number of cars going from Y to B will also be N2. Is this clear? So we have the number of cars for each route. Now we are trying to find out the time for each of these cases. So from A to X, it takes 12 minutes plus 3 minutes of an additional time for each car. So it is 12, the fixed time, and 3 minutes for each additional car. Why are we subtracting 1? Because whenever an additional car comes, then 3 minutes is added. So for the first car, it is 12. For the second car, 3 minutes is added for each car. So this is for one car, the travel time of one car, when there are n1 number of cars taking A to X. Similarly, for Y to B, this time is the same, 12 minutes plus 3 minutes for each car. So it will be 12 plus 3 times n2 minus 1. Is this clear? So this will become 9n1 plus, sorry, not plus, plus, yes, sorry. It will be 9 plus 3n1, 9 plus 3n1, and this will be 9 plus 3n2. Any doubt? Just check. Okay. So from X to B, each car takes 30 minutes, not each car, single car takes 30 minutes. Additional car increases the time by 0.9 minutes. So we have 30 plus 0.9 times n1 minus 1. Why are we taking n1? Because n1 is the number of cars traveling from X to B. And why n1 minus 1? Because each additional car increases the time by 0.9 minutes. So if you solve this, it will be 29.1 plus 0.9 n1. The travel time from A to Y. So if you go back, the travel time, sorry, if you go back, travel time for a single car is 30 minutes and each additional car increases the travel time by 1 minute. So it will be 30 plus 1 times n2 minus 1. N2 is the number of car traveling from A to Y and minus 1 because each additional car is increasing that time. So we'll have 29 plus n2. Is clear? Now you see the time taken to travel from A to B via X will be the sum of this and this. Similarly, time taken to travel A to B via Y will be summation of this plus this. So we'll just write it 9 plus 3 n1 plus 29.1 plus 0.9 n1. This will become 38.1 plus 3.9 n1. Is this clear? And this will become 9 plus 3 n2 plus 29 plus n2. We are adding this and this, so we'll have 38 plus 4 n2. So this is the travel time from A to B via X, and this is the travel time from A to B via Y. I hope this is clear. Now, for Nash equilibrium, a person should be indifferent of choosing from A to B, going from A to B via X and from A to B via Y. Therefore, we'll just equate these two. We'll say 3.8 plus 3.9 n1 is same as 38 plus 4 n2. We have one more equation which says that n1 plus n2 is equals to 4. And when you solve this, yeah, I have space. So this equation will actually become 0.1 equals to 3. So minus 3.9 n1 plus 4 n2. All right. So I'll write these two equations over here. N1 plus n2 equals to 4 and minus 3.9 n1 plus 4 n2 equals to 0.1. Is this clear? These two are the two equations. When we solve this, we'll get the solution. So we'll just multiply this equation by 4 and we'll get 4 n1, 4 n1, and this will become 16. And when you subtract it, it will be 0.1 n1. And okay, we are just subtracting it. So we'll just, this will be positive, this is negative, this is negative. All right. So this will become 7.9 n1 plus 0 is equals to 15.9. And n1 is approximately, you see, this is approximately 16, this is approximately 8. So it is approximately 2 and n2 is approximately 2. And this is why in the beginning of this problem, I told you that since the problem size is very low, these numbers are approximations and not the exact Nash equilibrium. Therefore, the action profile when two players are taking the route X and two players are taking the route Y is the Nash equilibrium for this game. So this is the correct answer. Any doubt over here? Aman, any doubt? Okay. So in this problem, this is actually linear problem. What it says is the consumer has a uniform distribution between the interval 0, 1. So I'll just draw the interval 0 and 1. And the consumers are uniformly distributed in this interval. There are 4 firms and each consumer will purchase 1 unit of good from the firms which is closest to him. So each consumer will find the closest firm and then purchase the good from that firm. If more than one firm are located in equal distance, the consumer will buy with equal probability from each of the firms. All right. So when more than one firm is located in at the same location, the consumer will buy with equal probability from each of the firm. You can just randomly choose one firm with equal probability. All right. For example, If one firm is at location 0 and three firms are at location 1, then the former captures 0.5 of the market. You see this line closest to them. So when one firm is at 0 and three firms is at 1, the consumers at this end will be closest to 0 and the consumers in this end will be closest to 1. All right. So 0.5 of the market, this consumers in this area will flock towards the firm at 0.0, and the rest of the consumers, so these are the rest of the consumers which are 0.5 in quantity, these will be evenly divided between the three firms. So this is the market share of each of the firms, the three firms which are located at 1. Can we say that the Nash equilibrium of each of the firms is to locate at 0.5? So the question is a yes, or you can also say cannot be determined. So the question is, if all the firms are located at 0.5, is this a Nash equilibrium of this game or not? Think about it. So how would you go about? So you see, you have to think about it in this way. If all the firms are located at 0.5, is there an incentive to deviate from this point? If yes, then this is not a Nash equilibrium. If yes, then this is not a Nash equilibrium. Will the firms at 0.5 deviate? And when will they deviate? If they have a higher utility when they deviate from this point, then they will deviate. So suppose, so you see this line is very important. The consumer will buy from the firms with equal probability. So actually it means that the consumer will be divided equally between all the three firms. This is the other interpretation of that. So when all the firms are at 0.5, the consumers in this end and the consumers in this end will all flock towards the firms at 0.5. So all the firms are there. Now all the consumers between 0 and 1 will be equally divided between the firms which are there at 0.5. So all the firms are getting 1/4 of the consumers. Now suppose a firm deviates from this point to any other point. So this firm will get all, so I'll just change the color. Since this firm is closest to all the consumers over here, so all the consumers over here will flock towards this firm. Because it says it will go towards the firm which is closest to him. So all these consumers will flock towards, suppose the firm name is firm A. So all the consumers from this end will flock towards firm A. And the consumers in between this value from 0.5 and to the value which A is actually moving to, half of these consumers will move to A and half of these consumers will move to the firms in 0.5 at the location 0.5, because that will be the closest to that firm will be closest to that customer. Half of the so at point in between the midpoint at one end, that those firms will be closest and the other end firm A will be closest. So firm A will get more consumers when he deviates. He will get all the consumers from this end and also some of the consumers from the other end. Therefore, there is a incentive to deviate. There is an incentive to deviate from this point 0.5, and therefore this is not a Nash equilibrium of this game. And this is the correct answer. So since one of the firms can deviate, then any of the firms can deviate, and therefore this is not a Nash equilibrium of this game. Think about what will be the Nash equilibrium of this game. So this is not a question over here, but I'm asking you what is the Nash equilibrium of this game? What will be the Nash equilibrium of this game? You see, that Nash equilibrium will be such that no firm has an incentive to deviate from the point which they are in. And if you have seen professor's lecture, that point will be equidistant from all the firms. So this point will be divided in 5 parts: 0.2, 0.4, 0.6, and 0.8. And the firms, suppose the firms are A, B, C, and D. If they are there in this form, then they will have no incentive to deviate from these points. Is this clear? All right. This is the problem of extensive form game. In the extensive form game, this is example is taken from professor's lecture. There is an entrant, so there's a firm which is known as incumbent, and he is already in the market, and a player wants to enter the market. Now he has to decide whether to enter or not. So I'll write entrant. He has a decision to make whether to enter the market or not enter the market. All right. So this is how the game is represented. If you have seen professor's lecture, you will just recognize this is a game tree. Now, when he doesn't enter the market, the incumbent doesn't have any strategy, or he doesn't have to do anything because the player is not entering the market. When he is entering the market, the incumbent can play two strategies. Either he can fight or he can accommodate. All right. And the utilities I have mentioned. What will be the utilities when these strategies occur? So when the incumbent enters the market and the entrant enters the market and the incumbent fights, the payoffs are -2, 2. So when he's entering, so this is entering and this is fighting, the payoffs are -2, 2. And when the entrant enter and incumbent accommodate, the player is actually the utility is actually 2, 4. So incumbent is accommodating and the entrant is entering, then the utility is 2, 4. Moreover, when the entrant is not entering the market, then the payoffs are 0, 5. So this is the game tree. You can also draw the game table. You can also draw the game table. So we have entrant and incumbent. For entrant, the two strategies are enter the market and not enter the market. For incumbent, the two strategies are fight and accommodate. All right. So when entrant enter and incumbent fights, the utility is -2, 2. When entrant enter and incumbent fight, the utility is 2, 4. And when entrant doesn't enter, the utility of entrant will be 0, 5 for both the strategies of incumbent, because there is nothing to do for incumbent. All right, so this is how the game is being played. The question is, find the Nash equilibrium of this game. All right, take a minute, think about it, and then we'll discuss. Remember, we are discussing about Nash equilibrium and not the equilibrium from backward induction. All right, be careful. I was just thinking about this point which I have mentioned, and these points are actually not dividing the area equally between the players. You see, the players from this area will come to firm D, and half of the players from this area will come to firm D. Similarly, this will be the area which is coming to firm C. This is the area which is coming to firm B, and this is the area which is coming to firm A. All right. So firm A and firm D are getting a little bit more consumers than B and C. So I had also not thought about what should be the Nash equilibrium of this game. I guess it will be equally divided between all the players. So we have to find those points such that the number of players the firms are getting are equally divided. And these points are not actually equally dividing the region between all the players. Firm A is getting more than firm B and C, and firm D is also getting more than firm B and C. I'll check this again. I'll check this again. That is what I was thinking. So I would request you to also think, and if you find something, you would let me know in the next class. Okay, so we are here in extensive form game. So you see, we are asked to find the Nash equilibrium of this game and not backward induction. So we'll not use this game tree. So this is known as game tree. Game tree. Okay, so we'll not use this game tree. We'll use the game table. Now we'll just find out the best responses. When player 2 is playing F, the best response of player 1 is to play N. When player 2 is playing A, the best response of player 1 is to play E. I hope this is correct. Again, so I'll just change the color. When player 1 is playing E, the best response of player 2 is to play A. And when player 1 is playing N, the best response of player is either F or A. So it can either be F or it can be A. All right. So where are the best responses intersecting? The best responses are intersecting at this point and this point. Therefore, enter, accommodate, which is this point, enter and accommodate, and out and fight. So I have written N, it can be out. So out and fight. So this and this both. Therefore, both A and B are the Nash equilibrium of this game. Any doubt? Both A and B are Nash equilibrium of this game. So actually, it was not N, it was out. Out, comma, fight, and enter, comma, accommodate. Both are Nash equilibrium of this game. All right. So this is a same problem. This problem is same. I'll just draw the game tree again. Now the question is, using backward induction, find, sorry, just typo. So using backward induction, find the equilibrium of this game. All right. So there is an entrant, and he will enter or remain out. So when he is remaining out, the payoffs are, when the entrant is remaining out, the payoffs are 0,5. And when he is entering, the entrant has two strategies, either to fight or to accommodate. When he is fighting, the payoffs are -2,2. And when he is accommodating, the payoffs are 2,4. All right. So this is how the game is being played. By the way, if you think about it, you see this incumbent, not E, incumbent, this incumbent is actually very powerful. He's a very big player. And this entrant is a startup. He wants to enter the market. So when he doesn't enter the market, the entrant doesn't gain anything, but the incumbent gains, because if he would have entered the market, there would have been some loss. Therefore, there is some utility which is positive for the incumbent, because the new startup is not entering the market. But when he is entering, he can either accommodate, both will have some utility, both are getting the consumers, but since incumbent is a larger firm, he will get a higher utility than the entrant. But when the incumbent fights, you see this entrant is a very small firm. He has to put money, put resources to fight with the large incumbent, large firm. Therefore, his utility is negative over here. And since incumbent is also putting some effort in fighting, he has also utility, but it is positive because he's a larger firm and he has the capability that incumbent has the capability to fight against the entrant. So this is how the what is the meaning of this utility functions over here. All right, this is how I have mentioned the utility function. Now you see that we have to use backward induction. Now, when using backward induction, we think that the players are rational and they have complete knowledge, common knowledge. All the players have everything is common knowledge. So the entrant know that the incumbent has this knowledge, and with this knowledge, if he will find out what will the incumbent do. So the incumbent, you see the incumbent's utility is actually mentioned in the second part. So his incumbent is the second player. So you see, sorry, when incumbent is over here, he will always accommodate and he will not fight because the utility of accommodating is more than the utility of fighting. All right, so the incumbent's best response, will not use the term best response over here, I'm sorry. The entrant know that when he enters, the incumbent will accommodate, he will not fight because he is getting a higher utility. The incumbent is getting a higher utility in fighting, in accommodating than to fight. Therefore, the entrant know that when he enters, the incumbent will accommodate. The utility for the incumbent is 4. Now, when he is not entering, when he is out, you see the utility which the incumbent will get is 5. Which the incumbent will get is 5, but the entrant will get a utility of 0. In the previous case, the entrant was getting a utility of 2. So the entrant will think, if I remain out, I will get a utility of 0. But if I enter, I will get a utility of 2, which is more than 0. Therefore, the entrant will enter, and since accommodation has a higher utility, the incumbent will accommodate, and this will become the equilibrium, Nash equilibrium. Enter and accommodate. Enter and accommodate will be the backward induction equilibrium of this game. Right? So this will be the correct answer for this problem. Thank you. If you have any doubt, you can just post in the discussion forum, and I will just think about this problem and we will discuss this problem in the next class, and then we'll proceed with the next class content. All right. So again, before leaving, I'll just give a brief introduction of myself. I am Shubham Keshri, and I am working with operations research, specifically integer programming. I am a PhD student at IIT Kanpur in the Department of Management Sciences, and I am one of the TA for this course. All right. So we'll meet next week. You can just leave the session now. Thank you.